Hello and welcome. Today we're going to dive deep into some of the most important topics in precalculus. Think of this as a comprehensive review and expansion of the foundational concepts you'll need for calculus. By the end of this video, you will be able to: first, analyze functions by determining their domain, range, and key properties like injectivity and surjectivity. Second, master trigonometric functions including the unit circle, identities, and angle sum formulas. And third, understand and solve problems involving exponential and logarithmic functions. We'll break each topic down, work through plenty of examples, and even give you some practice questions to solidify your understanding. Let's get started. Our first major topic is functions and their properties. By the end of this section, you'll be able to define a function, find its domain and range, and identify key characteristics like injectivity, surjectivity, and whether it's even or odd. So what exactly is a function? At its core, a function is a special kind of relationship between two sets of numbers. We call the first set the domain and the second set the range. The key rule is that for every single input from the domain, there is exactly one output in the range. You can't have an input that gives you two different outputs. Let's visualize this. Imagine two bubbles, one for the domain and one for the range. A function is like a set of arrows connecting points in the domain to points in the range. The rule is, each point in the domain must have one and only one arrow leaving it. For example, the function f of x equals x squared takes an input, x, and gives you its square, x squared. For any number you pick, there's only one possible square. So this is a function. Now consider the equation x equals y squared. If we try to write this as a function of x, we'd have y equals plus or minus the square root of x. For an input like x equals 4, we get two outputs, y equals 2 and y equals minus 2. This violates our rule, so x equals y squared is not a function. A great visual test for this is the vertical line test. If you can draw any vertical line that crosses the graph of a relation more than once, it's not a function. If every vertical line crosses at most once, it is a function. Now that we know what a function is, let's talk about its domain and range. These are fundamental concepts for understanding a function's behavior. The domain is the set of all possible input values, or x values, for which the function is defined. The range is the set of all possible output values, or y values, that the function can produce. When finding the domain, we're essentially looking for any restrictions. There are two main things to watch out for. First, you can never divide by 0, so if your function has a fraction, you must exclude any x values that make the denominator 0. Second, you can't take the square root of a negative number in the real number system. So if you have a square root, the expression inside must be greater than or equal to 0. Let's work through some examples to see this in action. Example 1. Find the domain of f of x equals 1 over x minus 3. Here we have a fraction. The denominator, x minus 3, cannot be 0, so x cannot be 3. The domain is all real numbers except 3. We can write this in interval notation as negative infinity to 3, union 3 to infinity. Example 2. Find the domain of g of x equals the square root of x plus 5. Here we have a square root. The expression inside x plus 5 must be non-negative. So x plus 5 must be greater than or equal to 0, which means x must be greater than or equal to negative 5. The domain is the interval from negative 5 to infinity, including negative 5. Example 3. Find the domain of h of x equals the square root of x minus 2 all over x minus 5. This one has both restrictions. First, the denominator x minus 5 cannot be 0, so x cannot be 5. Second, the expression under the square root, x minus 2, must be non-negative, so x must be greater than or equal to 2. Combining these, x must be greater than or equal to 2, but not equal to 5. The domain is the interval from 2 to 5, union 5 to infinity. Finding the range can be a bit trickier. Often, it's easiest to find the range by looking at the graph of the function. The range is the set of all y values covered by the graph. For example, let's consider the function f of x equals x squared. The graph is a parabola that opens upwards, with its vertex at the origin. The lowest y value on the graph is 0, and it goes up forever, so the range is all non-negative numbers, or the interval from 0 to infinity. So to recap, the domain is the set of all valid inputs, and the range is the set of all possible outputs. We find the domain by looking for restrictions like division by zero or square roots of negative numbers. Now let's explore some important properties that classify functions. We'll start with injectivity and surjectivity. First, an injective function, also known as a one-to-one function, is a function where every distinct input maps to a distinct output. In other words, if you have two different inputs, they must produce two different outputs. You can't have two different x values giving you the same y value. A great visual test for this is the horizontal line test. If you can draw any horizontal line that crosses the graph of a function more than once, it is not injective. If every horizontal line crosses at most once, it is injective. For example, the function f of x equals x cubed is injective. Any horizontal line you draw will cross its graph only once. The function f of x equals x squared, however, is not injective. A horizontal line like y equals 4 crosses the graph at both x equals 2 and x equals minus 2. Two different inputs, 2 and minus 2, give the same output, 4. Next, a surjective function, also known as an onto function, is a function where every element in the range is actually an output of the function. In other words, the range of the function is equal to its codomain, which is the set of all possible outputs we're considering. Every possible output value is hit by at least one input. Let's look at an example. Consider the function f of x equals x squared. If we define the codomain as the set of all real numbers, then this function is not surjective. Why? Because the range is only the non-negative numbers. Negative numbers are in the codomain but are never outputs of the function. However, if we redefine the codomain to be the set of all non-negative real numbers, then the function f of x equals x squared times is time surjective. Every non-negative number is an output of the function. Finally, a function that is both injective and surjective is called a bijective function. These functions are special because they have a perfect one-to-one correspondence between inputs and outputs. Every input has a unique output, and every possible output is produced by exactly one input. Bijective functions are the only functions that have inverse functions, which we'll talk about next. To recap, injective means every input has a unique output, which you can test with the horizontal line test. Surjective means every possible output is actually produced by the function, and a function that is both is called bijective. Let's continue our exploration of function properties by looking at even and odd functions. These classifications describe a function's symmetry. A function f is called an even function if, for every x in its domain, f of negative x equals f of x. This means that plugging in a negative number gives you the exact same output as plugging in the positive version of that number. Visually, even functions are symmetric with respect to the y-axis. If you were to fold the graph along the y-axis, the two halves would match perfectly. A classic example is f of x equals x squared. Let's test it. F of negative x is negative x squared, which is just x squared. And x squared is f of x. So f of negative x equals f of x, confirming it's an even function. You can see the symmetry in its parabolic graph. Now for odd functions. A function f is called an odd function if, for every x in its domain, f of negative x equals negative f of x. This means plugging in a negative number gives you the negative of the output you'd get from plugging in the positive number. Visually, odd functions are symmetric with respect to the origin. If you rotate the graph 180 degrees around the origin, it will look exactly the same. A classic example is f of x equals x cubed. Let's test it. F of negative x is negative x cubed, which is negative x cubed. And negative f of x is negative x cubed. Since f of negative x equals negative f of x, it's an odd function. You can see this origin symmetry in its graph. It's important to note that not all functions are even or odd. Many functions are neither. For example, f of x equals x squared plus x. F of negative x is x squared minus x, which is not equal to f of x or negative f of x. So, it's neither. To recap, even functions have y-axis symmetry and satisfy f of negative x equals f of x. Odd functions have origin symmetry and satisfy f of negative x equals negative f of x. Let's move on to a very important concept. Inverse functions. An inverse function essentially undoes what the original function does. The inverse of a function f is denoted f inverse of x. The key property is that if f takes an input x to an output y, then f inverse takes that output y back to the original input x. They are opposites. A crucial point. A function can only have an inverse if it is bijective, meaning it's both one-to-one and onto. If it's not one-to-one, the inverse wouldn't be a function, because one input would lead to multiple outputs. Visually, the graph of an inverse function is a reflection of the original function's graph across the line y equals x. This is because the inverse function swaps the roles of x and y. So how do we find an inverse function? There's a simple four-step process. First, replace f of x with y. Second, swap x and y in the equation. Third, solve the new equation for y. And fourth, replace y with f inverse of x. Let's try an example. Example 1. Find the inverse of f of x equals 2x plus 3. Step 1. Y equals 2x plus 3. Step 2. X equals 2y plus 3. Step 3. Solve for y. Subtract 3 from both sides to get x minus 3 equals 2y. Then divide by 2 to get y equals x minus 3 over 2. Step 4. Replace y with f inverse of x. So the inverse function is f inverse of x equals x minus 3 over 2. Let's verify this. If f of 1 is 5, then f inverse of 5 should be 1. F of 1 is 2 times 1 plus 3, which is 5. F inverse of 5 is 5 minus 3 over 2, which is 2 over 2, or 1. It works. Example 2. Find the inverse of g of x equals the square root of x minus 4. Step 1. Y equals the square root of x minus 4. Step 2. X equals the square root of y minus 4. Step 3. Solve for y. Square both sides to get x squared equals y minus 4. Add 4 to get y equals x squared plus 4. Step 4. Replace y with g inverse of x. So the inverse is g inverse of x equals x squared plus 4. Now there's a catch here. The original function g of x equals the square root of x minus 4 is only defined for x greater than or equal to 4. Its range is y greater than or equal to 0. For the inverse to be a function, its domain must be the range of the original function. So we must restrict the domain of g inverse of x to x greater than or equal to 0. The full inverse function is g inverse of x equals x squared plus 4 for x greater than or equal to 0. To summarize, an inverse function reverses the action of the original function. You find it by swapping x and y and solving for y. Remember to check if the original function is 1 to 1, and restrict the domain of the inverse if necessary. Great job on functions! Now, let's shift gears to our second major topic, trigonometric functions. By the end of this section, you'll be able to use the unit circle to define trigonometric functions, apply key identities, and use angle sum formulas. Trigonometry is the study of triangles, but in precalculus we extend it to the unit circle. The unit circle is a circle with a radius of 1, centered at the origin. Imagine an angle, theta, in standard position, meaning its vertex is at the origin and its initial side lies on the positive x-axis. The terminal side of this angle will intersect the unit circle at a point x, y. This point, x, y, is the key to our definitions. We define the cosine of theta as the x-coordinate of this point, and the sine of theta as the y-coordinate. From these two, we can define the other four trigonometric functions. Tangent is sine over cosine, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. This definition is incredibly powerful because it works for any angle, positive or negative, greater than 360 degrees, not just angles in a right triangle. Let's find the values for a common angle, 30 degrees, or pi over 6 radians. The point on the unit circle for this angle is the square root of 3 over 2, 1/2. Therefore, cosine of 30 degrees is the x-coordinate, square root of 3 over 2, and sine of 30 degrees is the y-coordinate, 1/2. Now let's try an angle in a different quadrant, like 210 degrees, or 7 pi over 6 radians. This angle is in the third quadrant. The point on the unit circle is negative square root of 3 over 2, negative 1/2. So, cosine of 210 degrees is negative square root of 3 over 2, and sine of 210 degrees is negative 1/2. Notice how the signs of the coordinates tell you the signs of the trig functions in each quadrant. So the unit circle provides a universal way to define and evaluate trigonometric functions for any angle. Now let's talk about trigonometric identities. These are equations that are true for all values of the variable for which both sides are defined. They are incredibly useful for simplifying expressions and solving equations. The most important identity is the Pythagorean identity. It states that sine squared of theta plus cosine squared of theta equals 1. This comes directly from the unit circle. The point x, y on the circle satisfies x squared plus y squared equals 1, which translates to cosine squared plus sine squared equals 1. From this one identity, we can derive two others by dividing by cosine squared and sine squared, respectively. Dividing by cosine squared gives us tangent squared of theta plus 1 equals secant squared of theta. Dividing by sine squared gives us 1 plus cotangent squared of theta equals cosecant squared of theta. Let's see how we can use these to solve a problem. Example 1. If sine of theta equals 3/5 and theta is in quadrant 2, find cosine of theta. We can use the Pythagorean identity. We have 3/5 squared plus cosine squared equals 1. That's 9/25 plus cosine squared equals 1. Subtracting 9/25 gives cosine squared equals 16/25. Taking the square root gives cosine of theta equals plus or minus 4/5. Since theta is in quadrant 2, where x-coordinates are negative, cosine must be negative. So cosine of theta is negative 4/5. Example 2. Simplify the expression secant of x minus cosine of x. This looks complicated, but we can simplify it using identities. First, rewrite secant as 1 over cosine. Now we have 1 over cosine of x minus cosine of x. To combine these, we need a common denominator. We can write cosine of x as cosine squared of x over cosine of x, so we have 1 minus cosine squared of x, all over cosine of x. The numerator, 1 minus cosine squared of x, is just sine squared of x from the Pythagorean identity. So the simplified expression is sine squared of x over cosine of x. So trigonometric identities are powerful tools for simplifying expressions and solving problems. The Pythagorean identity is the most important one to remember. Let's continue with another set of incredibly useful identities, the angle sum and difference formulas. These formulas allow us to find the sine, cosine, or tangent of a sum or difference of two angles. Here are the formulas. The sine of a plus b is sine a cosine b plus cosine a sine b. The cosine of a plus b is cosine a cosine b minus sine a sine b. And the tangent of a plus b is tangent a plus tangent b, all over 1 minus tangent A, tangent B. The difference formulas are very similar. For sine, you just change the plus to a minus. For cosine, you change the minus to a plus. And for tangent, you swap the signs in the numerator and denominator. Let's use these to find the exact value of cosine of 75 degrees. We can write 75 degrees as the sum of two angles whose trig values we know, 45 degrees and 30 degrees. So cosine of 75 degrees is cosine of 45 plus 30 degrees. Using the cosine sum formula, this is cosine of 45 times cosine of 30 minus sine of 45 times sine of 30. We know these values from the unit circle. Cosine of 45 is root 2 over 2, cosine of 30 is root 3 over 2, sine of 45 is root 2 over 2, and sine of 30 is 1/2. Plugging these in, we get root 6 over 4 minus root 2 over 4, which simplifies to root 6 minus root 2 all over 4. This is a powerful technique for finding exact values for angles that aren't on our standard unit circle. Example 2. Simplify the expression sine of x plus pi over 2. Using the sine sum formula, this is sine of x, cosine of pi over 2, plus cosine of x, sine of pi over 2. We know that cosine of pi over 2 is 0, and sine of pi over 2 is 1. So the expression becomes sine of x times 0 plus cosine of x times 1. This simplifies to just cosine of x. This is a very important identity that shows how sine and cosine are related by a phase shift. To recap, the angle sum and difference formulas are essential for finding exact trig values of new angles and for simplifying complex trigonometric expressions. Alright, let's move on to our final major topic, exponential and logarithmic functions. By the end of this section, you'll be able to understand the relationship between these two functions, apply their properties, and solve equations involving them. Let's start with exponential functions. An exponential function has the form f of x equals a to the power of x, where a is a positive constant, not equal to 1. The variable is in the exponent. The behavior of the graph depends on the base, a. If a is greater than 1, the function is increasing. It starts very close to the x-axis on the left and grows rapidly as x increases. If a is between 0 and 1, the function is decreasing. It starts high on the left and approaches the x-axis as x increases. In both cases, the graph passes through the point 0, 1, because any non-zero number to the power of 0 is 1. The domain of an exponential function is all real numbers, from negative infinity to infinity. The range is all positive real numbers, from 0 to infinity, not including 0. The x-axis, or the line y equals 0, is a horizontal asymptote. A very important exponential function is the natural exponential function. This is f of x equals e to the power of x, where e is a special mathematical constant, approximately 2.718. It's often called Euler's number and appears frequently in calculus and science. Now let's talk about logarithms. Logarithmic functions are the inverse of exponential functions. The equation y equals log base a of x is equivalent to the exponential equation x equals a to the power of y. The logarithm, y, is the exponent to which you must raise the base, a, to get the number x. Since logarithms are inverses of exponentials, their properties are flipped. The domain of a logarithm is all positive real numbers, from 0 to infinity. The range is all real numbers. The y-axis, or the line x equals 0, is a vertical asymptote. The graph passes through the point 1, 0, because log base a of 1 is always 0. Just like with exponentials, there's a natural logarithm. The natural logarithm, written as ln of x, is simply log base e of x. It's the inverse of e to the x. To recap, exponential functions have the variable in the exponent and show rapid growth or decay. Logarithmic functions are their inverses, telling you what exponent you need to get a certain number. Now that we understand what exponential and logarithmic functions are, let's look at their properties. These properties are essential for simplifying expressions and solving equations. First, the product rule. The logarithm of a product is the sum of the logarithms. So, log base a of m times n is log base a of m plus log base a of n. Second, the quotient rule. The logarithm of a quotient is the difference of the logarithms. So log base a of m divided by n is log base a of m minus log base a of n. Third, the power rule. The logarithm of a number raised to a power is the power times the logarithm of the number. So, log base a of m to the power of p is p times log base a of m. Let's use these properties to expand and condense logarithmic expressions. Example 1. Expand the expression log base 2 of 8x cubed. First, we use the product rule to separate the 8 and the x cubed. This gives us log base 2 of 8 plus log base 2 of x cubed. Then, we use the power rule on the second term to bring the 3 down. This gives us log base 2 of 8 plus 3 times log base 2 of x. Finally, we can evaluate log base 2 of 8, which is 3. So the expanded expression is 3 plus 3 times log base 2 of x. Example 2. Condense the expression 2 times ln of x plus 3 times ln of y minus ln of z. First, we use the power rule in reverse to move the coefficients back into the exponents. This gives us ln of x squared plus ln of y cubed minus ln of z. Next, we use the product rule to combine the first two terms. This gives us ln of x squared y cubed minus ln of z. Finally, we use the quotient rule to combine the remaining terms. The condensed expression is ln of x squared y cubed over z. These properties are incredibly useful for manipulating logarithmic expressions. Remember the three main rules: product, quotient, and power. Our final topic for today is solving exponential and logarithmic equations. This is where all the concepts we've learned come together. Let's start with exponential equations. The key strategy is to isolate the exponential term and then take the logarithm of both sides. This allows us to use the power rule to bring the exponent down. Example 1. Solve 3 to the power of x equals 10. The exponential term is already isolated. We take the natural logarithm of both sides. This gives us ln of 3 to the x equals ln of 10. Using the power rule, we get x times ln of 3 equals ln of 10. Dividing by ln of 3, we find that x equals ln of 10 over ln of 3. This is the exact answer. If you need a decimal approximation, you can use a calculator. Example 2. Solve 2 times e to the power of 3x minus 1 equals 5. First, we must isolate the exponential term, e to the 3x. Add 1 to both sides to get 2 e to the 3x equals 6. Then divide by 2 to get e to the 3x equals 3. Now, take the natural logarithm of both sides. This gives 3x equals ln of 3. Dividing by 3, we get x equals ln of 3 over 3. Now let's look at logarithmic equations. The key strategy here is to use the logarithm properties to condense the equation into a single logarithm. Then, we can convert the logarithmic equation into its equivalent exponential form to solve for x. Example 3. Solve log base 2 of x plus log base 2 of x minus 2 equals 3. First, use the product rule to condense the left side into a single logarithm. Log base 2 of x times x minus 2 equals 3. Now, convert this to exponential form. The base is 2, the exponent is 3, and the result is x times x minus 2. So 2 cubed equals x squared minus 2x. This simplifies to 8 equals x squared minus 2x. Rearranging gives a quadratic equation. X squared minus 2, x minus 8 equals 0. Factoring gives x minus 4 times x plus 2 equals 0, so x equals 4, or x equals minus 2. We're not done yet. With logarithmic equations, you must always check your answers. The domain of a logarithm is only positive numbers. If we plug x equals minus 2 back into the original equation, we get log base 2 of minus 2, which is undefined. So x equals minus 2 is an extraneous solution. The only valid solution is x equals 4. To recap, to solve exponential equations, isolate the exponential term and take a logarithm. To solve logarithmic equations, condense to a single logarithm and convert to exponential form. And always check your answers for logarithmic equations. Alright, we've covered a lot of ground today. Let's quickly recap the key concepts we've explored. First, we delved into functions and their properties. We learned to find the domain and range, and how to classify functions as injective, surjective, even, or odd. We also saw how to find the inverse of a function by swapping x and y. Next, we reviewed trigonometric functions. We used the unit circle to define sine and cosine for any angle, and we applied the Pythagorean and angle sum identities to simplify expressions and find exact values. Finally, we explored exponential and logarithmic functions. We saw that they are inverses of each other, learned their key properties, and used those properties to solve equations. These topics are the bedrock of precalculus and will serve you incredibly well as you move on to calculus. The more comfortable you are with these concepts, the smoother your transition will be. Thank you for joining me today. Keep practicing, and you'll master these topics in no time.